So let's get started again. It's been a long haul now, so we're close to the goal, which is lunch today. But so my voice is failing a little bit. But anyways, what we have been talking about now was a rather extended example to see how encapsulation and in particular how IP can provide connectivity over several different networks. So here we had a Ethernet network and a PPP network, which are interconnected by this gateway or router, which has connections both to the Ethernet and to the PPP network. And with the proper logic at IP layers and the proper routing tables and so forth, we can provide connectivity between any two nodes in this network of networks. Okay. So a little bit more from a abstract point of view. So this was the network we have been considering, consisting of three hosts. Host here, here, and here, and then one router. Okay. So a very simple protocol layout of this network, this physical network, would look something like this. So maybe we have a web server here, we have a router and a web server at the PC. And we didn't draw in the workstation here. So at the web server, we have HTTP, of course, TCP, IP, and Ethernet. So these are the protocols which are executed or in play when it comes to web traffic. At the server, there might be other protocols, UDP and so forth here also, but just for simplicity, we just draw these. At the router, which is in the middle, it has for sure an Ethernet layer because it's connected to an Ethernet network. So it has to have an Ethernet network interface. Yeah, that's given, otherwise it cannot be connected. And on the other side, it's connected to a PPP network. So it has to have a PPP network interface. And on top of that, it needs an IP layer in order to provide connectivity. It doesn't need a transport layer because it's not an end node. Okay. And then at the other end node, the PC here, it has a PPP network interface card because it's connected to a PPP network, IP, TCP, and HTTP. And then there is a web browser software running on top of that. So on the bottom here, we have like a protocol picture of the physical network on top. Questions? Okay. So now, the purpose of all these networks is to provide services to the layer above them. And one can also think of it as it's hiding the complexity of the network below it. So for instance, the IP layer here would not necessarily need to know that how Ethernet is transmitting frames over this cable here. Is it using these type of cables or some other cables, what type of modulation coding and so forth, because it could be different or different shapes, right? The IP layer doesn't care, right? As long as Ethernet does its work, it's happy, right? TCP would just like IP to hide all the complexity of the networks which are included in this transfer, right? So TCP does not really want to know what's going on at the IP layer. So it provides an abstraction of the underlying physical reality. The Ethernet, of course, has to take care of the physical reality. But once that's abstracted, the IP layer can look at this as just a way of transmitting packets. Okay. So network interfaces, Ethernet and PPP, provides transfer of frames to nodes connected to these networks. Okay. So one could see the lower layers here as providing two networks which is able to transmit packets, right? So here we have one network and here we have one network, but they provide the same type of service, transfer of packets or frames actually. So IP provides to TCP or UDP or whatever it's on top of it, unreliable packet transfer between nodes with IP addresses. And these could be nodes on the same network or on different networks. Doesn't matter, right? So IP provides this picture to TCP. It provides just a big network which is able to transmit IP packets, or packets rather. And it doesn't matter for TCP, or TCP doesn't care whether this is over one network or several networks, because that is all abstracted away by the IP layer to TCP. And TCP, on the other hand, provides a service to HTTP, which is transfer of HTTP messages end to end. Okay, so for HTTP, it looks like this or like that. So HTTP can just transfer back and forth, back and forth, back and forth, without any knowledge whatsoever of what's going on at the lower layers. Okay, so this is the power of it, right? Because you can imagine how difficult it would be to write a browser software that needs to work, that has to take into account all physical layers, right? The optical layer, the satellite layer, the Wi-Fi layers, and so forth, right? It will be a humongous piece of software, right? So luckily, that's not needed. Okay, so back to the OSI model. So remember, we have 7 layers here, or 1, 2, 3, 4, and then 7, 5 layers if you like. The top layers here are end-to-end protocols, and the lower layers here are based on internetworks or on different links here. Okay. So now we have, if you remember, we have gone from the top layer talking about earlier today about web traffic and so forth down to Ethernet and so forth. So that's the network interface layer. Now we will go down and talk quite a lot about the physical layer, and quite a lot, I mean maybe 2 or 3 lectures on this, and then start to work ourselves up the layers again, right? So now we have gone from the very cozy, nice world of web browsers, and now we're going to go down to the dirty, hands-on shuffling bits over physical channels. So we're going to be down in the basement here and talk about this, how this works, for some time. And by doing this, this is the first part of the project also. So now, after these maybe 1 or 2 lectures, you can definitely get started on your project. So again, on the physical layer, there is another type of model for communications called Shannon's communications model. This is something also that's part of the learning outcome, so you need to know these blocks and what the purpose of that is. And Shannon here takes a little bit of another perspective on things. This model really concerns about transferring bits from the source to the destination. Okay, so or in this language is source to sink. So we can think of this as going from point A to point B over a physical connection, over this connection, for instance. And Shannon, who was a true genius, was active during the last century. So he wrote his biggest piece in 1948 that put the foundation to something called information theory. So he's the founding father of information theory, just as Newton is the founding father of what we call classical mechanics, or Einstein for the modern physics, right? So what he was concerned about is that he would like to transmit, or he was concerned about the problem of transmitting information from source to sink, and information encoded in bits. And information that's encoded in bits could be encoded efficiently or not so efficiently. So for instance, if I have a text file, it's encoded in ASCII format into a bunch of bits. Okay, so if you have a text file, you also know that you can compress that without losing information. You can run that through your favorite zip software to get a file which is much smaller than the original text file, but it contains the same information. So information for Shannon was actually the actually essential bits in the message, not the representation of the message, which could be using bits which have no real value, doesn't carry information. So he was concerned about taking a text file here and reproducing it here at the receiver, but he would like to do that in the most efficient way possible. And one way to do that is not to transmit all these redundant bits, but only the information bits. So the first step in the transmitter here is called the source encoder, and we can think of this as data compression. So we take our text file, which has many bits, and we produce a zipped version of this, which contains fewer bits. Okay, but these bits are really, really important here. So the bits we have here are really important. Each bit is important here. The bits here, you can lose a few bits without any significant problem in reading the text. Okay, some character might be wrong, but we can still decode the text as humans, right? But anyways, here these bits are really, really important. So these needs to be reproduced perfectly, right, for things to work. Okay, so the problem is that we are transmitting data over a physical channel here, which is unpredictable. It contains noise, interference, and so forth. So transmission over the physical channel here can never be error-free. Okay, so there is a chance that we need to protect these bits before transmission. So we do data compression to get the essential bits, and then we protect the essential bits by the next thing, which is called the channel encoder. And then we produce new bits here. Actually, we have more bits here than we had here. Okay, because we need to protect, we put in extra control bits, if you like. But we do that in a structured way. Here there is some control bits, but they are in an unstructured fashion. So we first distill it down to bare essentials, and then add some protection. And here we have protection bits. And the purpose of the protection bits here is that if there will be errors from this point to this point, then this block here can find those errors and correct them. So the blue bits here, so the blue bits here are the same. Okay, that's the purpose of the channel encoder here, to protect the bits such that the channel decoder can find errors in whatever bits we have here and reproduce the same bits here. Okay, we continue. The signal that goes out on this channel here, you know, is some waveform, while the input here, you have bits here, ones and zeros. Okay, so the modulator here is some type of glorified digital to analog converter. So it takes the bits and produces a waveform which is suitable for the channel to be transmitted. Okay, and that waveform, there is one waveform which is suitable for this, another waveform which is suitable for Wi-Fi, a third one for optical channels, and so forth. Okay, so it very much depends on which medium we have here on the channel, how this modulator is working. Okay, but anyways, so we have here, okay, so maybe we should say something like this. We transmit some bits here in a nice waveform like this. Okay, so maybe this is 1, 0, 1, 1, for instance. Okay, but there is some waveform. Now this waveform then is transmitted over the channel, and the channel typically attenuates this signal and then adds noise to it. So what is received here is some, that was a really poor line. Okay, so what we receive is some distorted version of what we have transmitted. So maybe the receiver looks something, receipt signal looks something like this. Okay, and then is the purpose of the demodulator to look at this signal and try to decode the bits which were here in the diagram. Okay, and then we get some bits here, and maybe it figures out that the first bit was a 1 and then makes an error, and the second bit is a 1 also, even though it was actually not a 1, it was a 0, and then maybe it gets the third and fourth bit correctly. Okay, so we see here that the bits that we had here, which were 1, -1, 1, 1, or 1, -1 could be 0 also. So 1, 0, 1, 1, and now we get 1, 1, 1 instead. Okay, so there is an error here, and the error occurred here. We know that, but the receiver don't know this. So, oops. So the purpose then of the channel decoder is to inspect these bits and see, does this make sense? Okay, because there are some rules in this channel encoder that permits some of these sequences and disallows some other sequences. If everything works well, the channel decoder can say, aha, this bit looks very funny, right? I don't believe this. So let me flip that bit and see if that works. And then it flips that bit and say, now it makes sense. So let me correct that bit, or let me flip this bit and hope that this was actually the error that occurred. And it happens to be in this case. So then the blue bits here, the blue bits we had here, which are then actually the same up here as down here, because the channel decoder was able to fix the errors. And if the bits are here, what we can do then is data compression in the other way. So here we have the zip file and all the bits are correct, and we do unzip, and then we get the correct text files here. So these are actually the same bits. Even though, okay, so if everything works well, we might have errors here, but that's fixed by the channel encoder decoder, and therefore these bits will be the same, and then when we run unzip, we have the same bits here. Okay. Questions? Okay. So what we would talk now about is this block, how we do digital to analog conversion and how we do analog to digital conversion. And what we want to do is we want to design the modulator and demodulator such that there are as few errors as possible that occurs here. So we want to minimize the probability of bit error. Okay, so we want to design this and this in order to do that. That's one criterion. The second criterion that we would like to do is to maximize the number of bits per second we can transmit over the channel, because bit rate is nice, right? 1 megabit is better than per second is better than 1 kilobits per second. Third thing we would like to do is to, of course, make this all power efficient, and as we see, also bandwidth efficient. So we want to minimize the resources we need in order to do this. Okay. So let's talk about how to transmit bits and how to decode bits from waveforms. So how to convert bits to waveforms and how to convert waveforms to bits. So the simplest thing we can do is to transmit 1 bit. Okay. Once we figured out how to transmit 1 bit, we just repeat this and transmit 2, 3, 4, 5, 6 bits, etc., or in indefinite amount of bits. But to start to take the baby steps towards this full-fledged model, let's start by transmitting just 1 bit. Okay. So we're interested in binary transmission. Okay, binary means that we transmit bits, not just necessarily a single bit, but could be several bits. And we transmit them over this noisy channel. Okay, so here we have the modulator block, here we have the channel, and here we have the demodulator block from our previous slide. So the input to the modulator is M, the message, and the message here is very simple. It's a binary variable, so it can take on 2 numbers. Let's call it 1 and 2. Might as well be 0 and 1, +1, -1. Doesn't matter. It only takes on 2 values. That's the important thing. So it's a binary variable, whether it's 0s or 1s, plus or minus 1s, or 1s and 2s, as it is in this case, doesn't really matter. So let's take 1 and 2. These are the 2 possible options of M. No other option is possible. Okay. What is the modulator? The modulator is a digital to analog conversion. And since the input can only be 2 things, the output can only be 2 things. Right? because there is no randomization here. It's a deterministic device. If it gets m equals 1, then it outputs one signal. If it's m equals 2, it outputs another signal. So if m is equal to 1, it means that the output is S1, some signal S1. And if the input is 2, then the output is S2. So the modulator conceptually is a super simple device, right? It just takes some bits in and then produces the corresponding signal out. Okay. Then this signal S is going over the channel where it gets some noise, and then it becomes the received signal here, R. And then it goes through the demodulator. And the purpose of the demodulator is to look at R and make a guess on what M was. Because M was the transmitted bit. And then it makes a guess, M hat. Hat here is for estimate or guess. Has nothing to do with Fourier transforms here. So the hat here means only estimate or guess. Okay, so the demodulator task is, given the observation of the analog receipt signal, R of t, and knowledge that it could either be S1 or S2 that was actually transmitted, figure out or guess which M was transmitted. Okay? So a small example here then. We know that the transmitted signal S of t is either S1 when the transmitted bit is 1, or it's S2 if the transmitted message is 2. Okay. So the received signal R of t is the transmitted signal plus noise. Okay. What is preventing us from doing perfect transmission here is the noise, right? If there was no noise, we could just look at S and determine whether it's S1 or S2. And if it's S1, then we know that M is equal to 1. So if there was no noise, let's forget about the noise, then we could just look at R is equal to S. And if R is equal to S1, then we know that M is equal to 1. So we put M hat equal to 1. So the noise is the problem, right? If we have no noise, no problem. Okay. Now, suppose the transmitted signal looks something like this. We have signal alternative 1, S1, is simply just a positive pulse like this, with some amplitude and some duration t. And then S2 is the same thing, but the negative pulse t. So some amplitude A for S1 and some amplitude minus A for S2. Okay. Now, suppose the received signal looks something like this. So it's either S1 or S2, we know that, and then plus noise. And suppose it looks something like this. Okay. Now, if you the demodulator here, what should you do? Well, the demodulator looks at this blue, that's the receipt signal, and has to figure out what is M. So M hat, what should it be equal to? So if you the demodulator, what would you do? Let's do it a little bit simpler. Suppose that the noise is not so high, so this is what we received. what would you determine then? What should m hat be for the green line here? One? Yeah, exactly. I mean, the green here is closer to S1 than to S2. It's more similar to S1 than S2. So the reasonable choice would be, well, it's probably S1. And if it's S1, then m hat should be 1. Stands to reason, right? Okay. But the blue one here is a little bit more tricky. It's not so obvious which one is closer. Maybe it's a little bit closer to S1 than S2. Would you agree? Right. So, yeah, so maybe the blue one should be 1 also. But for sure, I mean, if you would ask me which one I would be more confident in saying, I would say the green one is, most likely 1. The blue one looks a little bit more fishy, but I still believe that it's 1 that's been transmitted. Okay. So now we did this with visual inspection, right? But how should we program a machine to do this type of inspection? Well, essentially, what we would like to do is to get the machine to do some type of identification. Look at the distorted signal here and trying to figure out, is it closer to S1 or to S2? Okay. So what we would like to do is to have a mathematical way to measure distance between signals. Okay. So is the blue one, is it closer to S1 or to S2? Well, let's measure the distance between the blue one and S1. And the distance between the blue one and S2, and let's pick the signal alternative which is closest to the blue one. Okay, and this is a brilliant idea, it turns out, and this is also known as the minimum distance receiver. So we compute distances, and then we pick the signal alternative which is closest, that is on the minimum distance to what we have seen, to the received signal. Okay. So what we want to do is to figure out a way to measure distances for signals. Okay? We know how to measure distances between points in space, right? We take a ruler or a tape measure and we measure it. Okay, so this is maybe 60 centimeters, this is 30, and so forth. But how can we find a meaningful distance metric for signals? Okay? There is, okay, and now we go down to the mathematics of things here. And to get to the heart of the matter here, we need to specify a few things, inner product, norm, and distance. And let's start to talk about the energy of a signal, and also for purposes which is not obvious now, but will be very convenient later on, we will look at signals as being complex valued. So basically it has a real part and an imaginary part, and these are signals themselves. So a complex signal consists of two signals, the real valued signal and the imaginary signal. Okay, so we have a signal X. Okay, so X is the signal, and we would like to compute its energy. So then E here stands for energy, and X here is the energy for signal X. So what we do then is we would like to find a number that characterizes this signal. So we take the signal, we take the magnitude squared of it, and we integrate that for all times. And then we surely get a number, assuming that this integral converges, which we will assume, right, from now on. And therefore we get a number. Okay, so that's the energy. Okay, good. Next thing, inner product. What is that? The inner product is a number which relates two complex signals with each other. And it's defined by these angular, so notation-wise is this angular parenthesis, and we have two signals, x and y, and we would like to produce a number. That's what we call the inner product. So the inner product is we take x and we take y, and star here is complex conjugation. Okay. So we take x and multiply with y conjugate, and then we get something, and then we integrate that and we get a number, typically a complex number. Okay? But that's what we call the inner product. So x comma y gives this inner product. So the order of x and y is important here because, oops, we see that we conjugate y, not x. So the order is important. Okay. Continuing, the norm or the length of a signal, and now we're starting to get closer to distance, is defined as follows. We take x and we take double bars here. Okay, so that's the norm. And it's defined as the square root of the inner product of x with itself. Okay, inner product of x with itself, what is that? Well, if y is equal to x, is the integral for x times x conjugate, which is x magnitude squared. Okay, so it's the square root of this integral, and this integral we recognize as being the energy of x. So, the length or the norm of x is the square root of its energy. And this is a real valued positive number. And why is that? Well, it's because magnitude squared is a positive number, and we integrate that, we get a positive number. Possibly 0, but not negative. Therefore, it's safe to take the square root of it, and at least, well, safe, it's always safe, I guess, but it will produce a real valued number. Okay. So this is a number between 0 and potentially infinity, but it's never negative. So that's nice, because then a length, as we think of it, is a positive number, right? The distance, okay. Now, so we did all this work in order to produce a distance metric between two signals. So the distance between two signals, d for distance, and then x and y, two signals, is the length of what? The difference between them. Okay. So if x is equal to y, it would be length of 0, and the length of 0 is 0. If x and y are widely different, then x minus y would be a signal with large energy, and it would have a large norm, and therefore the distance would be large. Okay, so the distance between x and y is the norm of x minus y, and it's like this. Okay, so for instance, you are familiar with this. If we have 2 points, and now we have a vector representing this point and this point. So this is two-dimensional vectors, two-dimensional vectors. And suppose we have the origin here. We have then this vector. Oops, this is very clumsy written. And we have y. What is the distance between the points x and y? Well, we form the vector x minus y. Then we get this vector. And then the distance is the norm of x minus y. Okay, so it's simple geometry if you go back to your vector thinking, right? So the distance between 2 points is the length of the difference between these 2 points, these 2 vectors. And it's exactly the same thinking here. The distance between 2 signals is the length of the difference between the distances, the signals. As a matter of fact, we can view signals as being vectors in an abstract vector space, which we will do a little bit later. Questions so far? Okay. So, going back to this here, what do we need in order to figure out whether we should choose m equals, take the blue signal here, for instance. What should we do in order to figure out if m hat should be 1 or 2? Well, we compute the distances. So we compute d1, which is the distance between r of t and what signal number 1. And then we compute d2, which is the distance between r and s2. Okay, I did squares here because let's get rid of the squares. Sorry, so let's take them out like this. Okay. Okay, so we compute these two distances, which is taking the blue curve minus the S1, magnitude squared and integrate, we get D1. We take the blue curve minus S2, we get a new signal, magnitude squared and integrate, and then we get D2. And then we look at D1 and D2, and we pick the smallest one of them. So if D1 is less than D2, then we set m hat is equal to 1. So we take R minus S1 to compute D1. We take R minus S2 to compute D2. We compare D1 and D2. And if D1 is less than D2, that means that R is closer to S1 than to S2. And therefore, we think S1 was transmitted. And if S1 was transmitted, then we know that m is equal to 1. And the other way around. So, what do we do? Given the signal alternatives, sorry.
Excuse me?
Yes. Oh, okay, thank you. So let's go through the mathematics on Friday, which is tomorrow. And it's going to be brilliant because it's going to be between 3 and 5. Perfect start of the weekend. See you then.